things to look out for. One is the sample sizes are small, that is less than 30, and we don't know population variances. So if we don't know population variances, we estimate population variances, and in this particular situation, we have to make an assumption. There's no choice there. We have to make an assumption that the populations have equal variances. There's no way forward. So you can say that, sir, what if the population variances are not equal? The answer to that is that we will assume. And you would say, sir, what if the assumption is wrong? The assumption is wrong means we can't perform a test over here. We can only perform a test with an assumption that populations have equal variances. So there's a big, you would say, assumption or supposition, which should not definitely apply to all of situations, but we would have to make that assumption to move forward. So guys, the important thing over here is that I can't perform a test, guys. I can't perform a test. So I make an assumption that both populations have equal variances. And when will I make this assumption? I will make this assumption when I will notice two things. Sample sizes small. I will notice this one thing. And population variance not known. If I spot these two things in the question, that sample sizes are small and population variances are not known, then I'd know that I'm going to have to go for pooled estimate of population variance, combined estimate of population variance. This formula is already given in the formula sheet, but this is pretty much in correlation to that. If you just compare it with that formula, you get to identify that you are just doing summation of the entire data together. So sigma x minus x bar whole square plus sigma y minus y bar whole square is actually the sum of difference of, or sum of deviation square of data from the mean value. So that's what the numerator is. And since there was only one set of data, we had n minus 1. Over here we have n1 minus 1 plus n2 minus 1, which simplifies as n1 plus n2 minus 2. So, but this is the formula for the pooled estimate. So we've already identified we're going to do this when we spot small sample sizes with unknown population variances. If that be the case, we're going to use the pooled estimate, and we'll assume that both populations have equal variances. And this will be our formula. And this formula is given to you in the formula sheet. Now, basically what happens is that sometimes examiner might end up giving you the individual estimates of population variances, or might end up giving you sample variances. So you should be able to rearrange these formulas into those forms. So if this is sigma x minus x bar whole square, that sigma square as sigma x minus x bar whole square over n minus 1. So if I rearrange this equation, so I realize that sigma x minus x bar whole square is n minus 1 times sigma square, where sigma square is the individual unbiased estimate of the population variance. So if examiner gives us individual unbiased estimates, we can't use different variances when sample sizes are small. So we'd have to find still a pooled estimate. So we can say that sigma x minus x bar whole square must be equal to n1 minus 1 times sigma square and n2 minus 1 times sigma square, whole divided by n1 plus n2 minus 2. And then, guys, you also did this formula of unbiased estimate, that unbiased estimate of population variance is n upon n minus 1 sample variance, which is s square. So I can also rearrange it, and I can see that if I cross multiply this on the other side, I can see that n minus 1 sigma square equals n s square. So n minus 1 sigma square is replaced as n s square, n1 s1 square, and n2 s2 square. What you have to remember is that, sir, if I know estimates of population variances, then I have to multiply them by n minus 1 in Apple And if I know the sample variances, then I have to multiply them by n and then add them. So I could do this, or I could do this. So guys, with that being done, let's look at this particular example where for a single sample mean, I had to find out the confidence interval. So I found the unbiased estimate of the population mean, I found the unbiased estimate of the population variance, and I applied the formula for the confidence interval. And remember that since you're using small sample size with unknown population mean, and you're using an estimate, so you have to use the t-distribution. That was one part of it. More importantly, we did this question for the second part. So if you realize these are small sample sizes, if you realize we don't know the population mean, that's the two things you have to look for. You don't know population variance, and you have a small sample size. That will take you towards pooled estimate and t-distribution. So you know that you have to find out the pooled estimate. What I've done over here is that I have both the sample variances as well as both the estimates of the individual population variances. The reason I did that was that I could give you a bit of a comparison as well. Okay, you can use this formula as well, or you can use this formula as well. So you know that the combined variance is sigma 1 square over n1 plus sigma 2 square over n2. But what if, since we're assuming that sigma 1 square is equal to sigma 2 square is equal to sigma square, and they have equal combined variances. So this becomes sigma square over n1 plus sigma square over n2. And can also be simplified as sigma square 1 over n1 plus 1 over n2. This is the variance of difference of sample mean. So hence the standard deviation would become what? Sigma under root 1 over n1 plus 1 over n2. And that's what I've done over here. So if you look at this particular question, we have done sigma 1 over n1 plus 1 over n2 under root. So this is how this formula for value of t simplifies. So it's the same thing. I mean, you learned that in S1, that z is equal to x minus mu over sigma. And I told you that t is not different, x minus mu over sigma as well. So if you look at this formula, this is still the same formula, but we're just applying it to a difference of sample means. And that's why instead of single standard deviation, you're taking sigma over n1 plus sigma over n2 and under root. So for sample mean, it becomes sigma over under root n and sigma over under root n, and that's why you have this particular form of it. So I knew, I mean, I'm performing a hypothesis test, and the question was that if it's at 10% significance level, you had to check whether there's a difference. So it's a two-tailed test. The difference sample mean is equal to 0 or not equal to 0. So we found the critical region, and then we had the test value of the sample means. We put that in calculated the value of t that's coming out in the non-critical region H0. So H0 is going to be accepted, and hence there's no difference in sample mean.